My name is Makena. I'm a geologist currently working as a graduate consultant. My esteemed co-authors are Dr. Vera Miljanovic-Tamadit and Dr. Martin Kalinowski, both working for the CTBTO. Dr. Vera is the head of software integration, while Dr. Martin is one of the 2023 SnT coordinators. Their valuable contributions greatly enhance the quality of this work. I would have loved to join everyone for the in-person meeting, but due to some unavoidable circumstances, that was not made possible. However, I do look forward to opportunities to collaborate with you in the future. Without further ado, I'll delve into the presentation. Let's take a look at the CTBTO and IMS data. The current Provisional Technical Secretariat, the PTS, includes 3 verification divisions. We have the International Monitoring System, the IMS. We have the International Data Center, the IDC. And we have the On-Site Inspection Division, the OSI, as illustrated by the image. The CTBTO receives, collects, processes, analyzes, reports, and archives data from IMS facilities. This data is made available to authorized users. Automatic processing methods and interactive human analysis are used to produce and archive standard IDC products. The primary purpose of IMS data is nuclear explosion monitoring. In addition, IMS data plays a crucial role in various scientific and civil applications, including disaster risk reduction and climate change research, which is the basis of this presentation. The IMS data also aids in earthquake monitoring, tsunami early warning systems, volcanic eruption prediction, nuclear accident detection, and contributes to sustainable development efforts. Moving forward, let's take a look at the IMS data and climate monitoring. The IMS utilizes 4 monitoring technologies, which are seismic, hydroacoustic, infrasound, and radionuclide, as illustrated by the images. Seismic is used to listen or monitor underground activities, while hydroacoustic is used for underwater monitoring. Infrasound is used to listen above ground, while radionuclide sniffs for radiation. Let's take a deeper look into how these technologies can be used for climate monitoring. As mentioned, the IMS utilizes 4 monitoring technologies. The following are ways in which IMS data contributes to climate research and climate change monitoring. Let's take a look at infrasound technology and how it contributes to climate change monitoring and research. While infrasound technology registers man-made and natural events such as iceberg calving, glacier movements, storm activity, which can be used as indicators of climate change. It also monitors landslides and avalanches as climate change indicators. It can also be used to determine atmospheric property variations for climate change monitoring. Meteorological data such as external temperature, absolute pressure, wind speed, and wind direction collected from infrasound stations can be analyzed to enhance climate change studies. The following images illustrate how infrasound technology detects changes above the ground. Next, we have radionuclide technology and how it contributes to climate research and climate change monitoring. The radionuclide technology measures concentrations of natural radionuclides to track air mass transport and validate atmospheric models. It also monitors stratosphere and troposphere exchange and also validates global climate models. Radionuclide technology tracks seasonal and yearly variations of radionuclides connected to climate variations. It can also be used to analyze dust, pollen, chemical contents, and solar activity changes for climate change studies. Illustrated by the images below, you can see how the radionuclide technology is used to monitor and measure concentrations of the radionuclides. Let's take a look at hydroacoustic technology and how it contributes to climate research and climate change monitoring. Hydroacoustic technology uses background noise data for research on ice shelf breakup and warming. It also improves weather prediction and estimates through ocean temperature interference. Hydroacoustic technology can be used to study ocean processes, marine life, and whale populations affected by climate change. It can also be used to measure water temperature by acoustic thermometry for climate analysis. Illustrated in the images, we can see some of the hydroacoustic monitoring stations, and we can also see how some of the applications of the hydroacoustic technology, such as studying marine life. We can see the migration routes and interbreeding areas for marine life, such as, I think this illustration is for whales. Lastly, let's take a look at seismic technology and how it contributes to climate research and climate change monitoring. Seismic technology aids in acquiring and disseminating earthquake data and earth structure research. It can also be used to study glacier melting and its impact on seismic signals. We can use collocated seismic and infrasound stations to analyze wave travel time in the low atmosphere for climate change studies. Illustrated by the images, we can see how seismic technology is used for underground monitoring. These technologies, these IMS technologies offer valuable insights into climate change research by monitoring various indicators, validating models, and studying Earth systems and phenomena. Harnessing the potential of IMS data enhances our understanding of climate change, facilitates effective mitigation measures, and supports the development of resilient communities. IMS and IDC products help scientists better understand and prepare for the impacts of climate change. The image visually represents the inflow and outflow of monitoring data in products. The inputs are the raw IMS data, which are collected at monitoring stations and arrive in Vienna for IDC processing and analysis through the Global Communications Infrastructure, the GCI. The outputs are the data products created by the IDC and are generated volume specific timelines. The IDC and IMS products are made available to authorized users through the Virtual Data Exploitation Center, the VDEC, which is both an IT platform and legal framework that makes the CTBTO data and products available to scientists, researchers, and institutions around the world. VDEC helps facilitate the use of data and products in disaster warning and scientific studies. Scientists from many different disciplines have the opportunity to conduct research and publish new findings based on the CTBTO's IMS data. Benefits of IMS data for climate studies include accurate monitoring, global coverage, the early warning system, which enables early detection and prediction of extreme weather events, aiding risk mitigation and saving lives. We have climate modeling and prediction. IMS data supports simulation of future climate scenarios and assessment of potential impacts for effective adaptation and mitigation strategies. We have verification of climate agreements, scientific research, and policy and decision making. IMS data provides objective scientific evidence for informing climate-related policies, sustainable practices, and mitigation and adaptation strategies. IMS data varies depending on the source of the signal. Hydroacoustic data is the example used in this slide to illustrate this. As you can see from the images, different reports have been generated depending on the source of the signal. This is one of the benefits of using IMS data since it offers accurate monitoring. The Hungatunga Hunga Apai eruption is an example of how IMS data has successfully been used in scientific research. The volcanic event of 15th January 2022 was by far the largest event observed on the infrasound network to date. All 53 installed stations recorded it. It was also recorded by seismic and hydroacoustic stations. The pressure waves are seen to propagate several times around the globe for at least 4 days. A lot of research is being published with IMS waveforms, observations of this unique event. Promoting the peaceful use of IMS data for climate studies requires a collaborative and inclusive approach. The key strategies include international cooperation. We should foster collaboration between countries, research institutions, and international organizations. We should encourage dialogue, share data, expertise, and resources. Capacity building is another strategy. We should invest in training and educational programs to enhance technical skills and knowledge of researchers, policymakers, and stakeholders. The SnT is like a wonderful example of this. Another strategy is data accessibility and transparency. We should ensure open access to IMS data for authorized users while maintaining data security. We've already discussed about the Virtual Data Exploitation Center. Another strategy is public awareness and engagement. We should raise awareness about the importance of IMS data for climate studies through campaigns, forums, and media outreach. We should encourage public participation in climate discussions. The next key strategy in promoting the peaceful use of IMS data for climate change monitoring is policy advocacy. We should advocate for integrating IMS data into national and international climate policies. We should engage policymakers and collaborate with stakeholders for evidence-based decision making. Another strategy is multidisciplinary approach. We should encourage collaboration between experts from various fields to explore explore complex climate change interactions. We should foster a holistic understanding of impacts and solutions. Promoting the peaceful use of IMS data for climate change monitoring can also be achieved through long-term commitment. We should sustain support and funding for IMS data utilization. We should invest in research, infrastructure, and technology advancements. We should monitor, evaluate, and improve effectiveness. Implementing these strategies enables peaceful use of IMS data, fosters international collaboration, and contributes to informed decision-making for climate change mitigation and adaptation. In conclusion, implementing IMS data in climate change studies can enhance our understanding and response to climate change. IMS data contributes to climate research and climate change monitoring by detecting atmospheric events, verifying emissions reduction efforts, monitoring oceans, improving climate modeling, studying long-term trends, and promoting collaboration. By raising awareness and promoting the peaceful use of IMS data for climate studies, we can garner support for this important cause while contributing to the global effort of achieving the universalization and entry into force of the CTBT. Thank you for your attention.
Okay, applause to that. Yeah, thank you so much, Riungu. The next one is about the climate change and global security nexus, prospects for CTBTO. It will be presented by Sweta Basak. This is correct?
Yes,
Sweta
perfect.
Basak.
I would like to speak from here. Can you please, am I audible now?
You can do, okay.
Yeah.
She is a PhD student from Jawaharlal Nehru University, and she's talking about the use of the IMS data and then the climate change. Please, the floor is yours.
Thank you so much. I am from humanities background and all my panelists are from science background. So my presentation might be a bit from the perspective of humanities, from the perspective of international relations and diplomacy. And that can be a bit different. So it's a disclaimer. So today I'm going to talk about climate change and global security nexus and prospects for CTBT. I come from India, and India is not a party to the treaty, but whenever I come across this aspect, the first thing I search is what can be the probable prospects of partnership with the country where my country can actually learn and know about the scientific aspects of CTBT. Because back in India, if we say about the treaty, they took it from a political perspective. They took it from a very political aspect and see the geopolitical concerns, the strategic concerns. But most of the time, what is missing in the discourse about CTBT in India is the scientific, the verification regime the treaty actually has. In the popular discourse, people don't know about it, and it is not even highlighted. But as in the academics, I intend to see that after so many years of not being together, what can be a prospect to be together or to foster partnership with the treaty. In my presentation, I would like to touch upon two important aspects. To begin with, the presentation will explore the correlation between climate change and global security nexus, and will sketch out the prospective contribution of CTBTO, which can make to this issue. Furthermore, there will be analysis of prospects for the IMS data for the confidence building measures, like for countries which are not a part of the treaty, like India. So first we need to know the threat. What is the threat? The climate change. Nature does not discriminate between big power, small power, middle power, or the third world or the first world. Climate change affects the capabilities and the operational concerns of a state, in addition to acting as a threat multiplier. Currently, nations are becoming more conscious of the problems caused by environmental degradation and global warming. So in the geopolitics, when we talk about conflict, we talk about nations are in conflict, we see the strategic aspects, but most of the time what we forget are the climatic or the environmental baggages the conflict is coming with. The first thing, for example, in 1992, when the Kuwait crisis happened and the Iraqi army attacked Kuwait, they burned a lot of oil wells, which caused massive air pollution, and it was mostly the widespread it was covered by the media in a widespread way, which showed that what conflict can come up with. Even now in the world, we are seeing the Ukraine and the Russia has attacked Ukraine, and the war has been here for a year. But we are talking about the geopolitical aspects, we're talking about the politics of the war, we're talking about countries, but what we are forgetting is the impact of the war on the biodiversity. The impact of the war on the biodiversity, the loss of biodiversity is facing. For my PhD, I'm working on Iraq and its climatic impact of the civil war. So there as well, we have observed that in the entire Mesopotamian marsh region was extinct due to the war. So once we talk about the war, we forget about the impacts, the environmental impact of it, and most of the time, what we also ignore is that how this environmental impact is prolonging the war, making the war stay for a longer time. Another example I can give in that regard is Yemen. Yemen is in the civil war, facing the civil war for years, and now it is facing the most pressing food crisis and the water crisis. But why it is prolonging? Because the water resources are given by the Houthi by the rebel groups, and that's why people are supporting those rebel groups, and no negotiations are coming into place, because so resource management and conflict, these nexuses have been always there. In the view of this, there are nations aiming to boost the use of renewable energy, improve energy efficiency, endeavoring to lower carbon footprint and prevent escalating climate-related conflicts and crises as it works for redefining the relationship between climate change and security. So we know what is climate change, what is global warming. Just for the sake of the presentation, I have written it. I will not go into it much. So now I would like to highlight about the climate change and the discourse of security. So there is a growing awareness that climate change poses a security risk. The relationship between climate change and security has been considered by the United Nations Security Council has been considered by the UNSC and a part of most of the national security strategy of many countries, like the US, the China. They all have this. They have included environmental security as a major aspect for their national security strategy papers as well. It is necessary to comprehend the relationship between climate and security by defining the risk and resilience, which frequently represents a vicious cycle of fragility, climatic vulnerability, and human insecurity. Climate change measures can improve a society's ability to adopt the environment and create avenues for increased peace and security. These initiatives include developing local ability to translate early warning and climate-informed advisories, early warnings for food security planning, climate-smart mapping, adaptation of planning, safety net programs, and risk financing. To end this vicious loop between climate change and conflict, integrate climate actions with peace goals, and so support a climate-resilient peace. Other adjustments and interventions are also required. And in this regard, CTBTO can play a crucial role. So now I'll talk about a bit of the prospects of CTBT. CTBT has, in climate change, to deal with climate change. So as we all know, that CTBT has already working efficiently to make the world safer, even if it has not come to force through ratification. It is not only serves as a powerful brake on the nuclear proliferation, but stopping the development of more lethal nuclear weapons and halting the hazardous spiral of international nuclear competitiveness. The CTBT significantly aids in preserving and maintaining the environment by putting an end to the nuclear test explosions since 1996. So we have in CTBT, we have the International Monitoring System stations, which gathers up the signal for a wide range of natural phenomena while continuously searching for indicators of nuclear explosions in violation of the treaty. These data are widely regarded as being exceptional and gold mine of knowledge with several civil and scientific uses. We all know about the seismic, the hydroacoustic, and infrasound. There are scientists who can talk about it. I am just not the correct person to mention about them. So the ability of this IMS system to track the atmospheric disturbance where volcanic eruptions and severe storms and other large-scale turbulences provides a way to improve weather forecast. And by using nearly 2 decades of accumulated data to track climate change. Scientists have presented their findings about the IMS data about for climate monitoring application. And the region from I come, the South Asian region, is the most vulnerable to such disasters. Like every year we are seeing frequent storms, like in Bangladesh, in the coastal region of India. Bangladesh is the most impacted. And being a developing nation, they are facing the cons of it every year. The IMS data for climate, so there are some aspects which CTBT is working on, like the identification of signals from atmospheric storm, tracking icebergs with hydroacoustic arrays of international monitoring system, global infrasound from non-linear ocean waves, etc. Along with other United Nations and international entities housed in the Vienna International Center and globally, CTBT also seeks to minimize the environmental impact in its everyday operation. As an organization, CTBT is also trying to foster sustainability and sustainable developmental goals. Like yesterday, I attended a session. There was a talk that how CTBT as an organization is also becoming climate resilient, sustainable. Like it's adopting solar panels in their offices and some interesting developments like the IMS stations in New Zealand or in Kiribati, these islands, they are following the environmental protocols of those regions and making their stations as per that. So the International Monitoring System, which is a global network of cutting-edge monitoring facility, is used to demonstrate the compliance of CTBT. IMS data may also help the mankind with wide range of other ways, from monitoring climate change to assessing the early tsunami warnings to enhance the global response capabilities in the case of nuclear disaster. At a time when the world is dealing with several crises that threaten the norms and the institutions that were established to enhance international peace and security, CTBT can also play a very crucial role. So the role of CTBT, so to conclude, the role of CTBT in minimizing the disproportional impact of climate change, nuclear tests, and nuclear hazards are praiseworthy. To conclude, the CTBT is contributing to multiple aspects of climate change mitigation by adopting measures like building multi-level governance framework to support peace, development, and humanitarian nexus, finding ways to integrate climate change evidence in early warning and early action systems, designing coherent adaptive features and programs, and building innovations and social capital. Before we end up like this, I think we should praise what the organization is doing, and I believe that after 10 years or so, when my kids will come to the SnT, India will be part of it. Thank you so much.
Okay, thank you so much, Sweta. You're very enthusiastic because you're very young. That's very nice. That the hope for the realization that is the future. That and very enthusiastic. Wow, sometimes hard to follow what to say sometimes, but really, we got it. So, any question from the room? Now, I would like to enhance that. You highlight the use of the IMS data to the climate change to assess that. So that you think that, how will be the role of state signatories in that? Because CTBT is an organization. So we are doing what we have to do based on the treaty. But from your side country, what is your perspective on using those data available for you?
Like in the opening session, Madam, I don't know, Kris, she talked, your head of the institute, what is her name, I forgot.
Madam Rita.
Yeah, Madam Rita, she mentioned about the cross-verification, like we have the technologies, but we're verifying with the CTBT as well. That's why she made a MOU as well 2 days back. So I think this cross-verification is also needed. India also has this technology, but even, for example, if there is a storm in the western coast of India, Pakistan also talks who don't talk, who are like the enemy nations. So I think these are the prospects where actually there can be a melting point where all stakeholders can talk. That's why I'm emphasizing that the climate change can be a reason where India and CTBT can again come together.
Okay, good.
Thank you.
Thank you so much. If there is no question from the room, let's move to the next one. It will be by, let me check it here in my note here. Yes, it will be about the comprehensive report on the magnitude 7.5 from the 14th of December 2021 in Flores earthquake. It is about the tsunami. Let's move to tsunami now. And then they are talking about the early warning and aftershock distribution. It will be done by Kris Astra. Kris, we call Kris. Yeah, it's a seismologist from the Indonesian Meteorological, Climatology and Geophysics Agency. So, the floor is yours. You can go ahead there. Yes. You can go over there. No, you can stand on. Did you bring it for the okay, the pointer? Yeah. Okay, good.
Okay, thank you very much, Professor Geralds, for the time. Good morning, good afternoon, ladies and gentlemen, dear scientists, experts, colleagues, and friends. My name is Kris Astra. Of course, you can call me Kris. I would like to present my comprehensive report on magnitude 7.5 on 14 December 2021, Flores earthquake, rapid observations, tsunami early warning, and aftershocks distributions. Okay, during the time, a warm warning in the Flores region, Indonesia, was shocked by a strong ground motion that felt widely almost in all eastern Lesser Sunda Island and southern Sulawesi of the Layer Island. The island hit by magnitude 7.5 on 14 December 2021 on 3/2023 UTC. And by report, the city of Ruteng, one of city nearby, in Labuan Bajo, Larantuka, Adonara, Lembata, felt the shaking reaching 4 scale of MMI, or modified Mercalli intensity. Moreover, several cities in Sulawesi Islands, such as Makassar, Takalar, and Pangkep, reported felt 2 to 3 MMI intensity level, while in Denpasar, in Bali Island, far away from them, is observing 2 to 3 MMI. The earthquake caused 1,161 house damages and 16,593 people were evacuated in Selayar Island, urgency. We are in BMKG, or Indonesian Meteorology, Climatology and Geophysics Agency. Regarding the real-time seismic monitoring, we use continuous seismogram data from our agency. The network has 586 seismic instruments, which consists of 440 Indonesian located broadband seismometer, including 5 number of borehole seismometers and 6 CTBTO seismic stations, while 167 seismometers located and owned by our neighboring countries. Okay. The earthquake signal initially recorded by 4 nearest stations of LRTI, EDFI, PSGM, and ALKI, and then produced the first auto-location of this event. The earthquake parameters keep updated by the seismologist on duty in line with the incoming signal from the rest of seismic stations until reaching the parameter stability. Our agency, BMKG, operating 669 accelerometer sensor in Indonesia, and the main event detected clearly by 31 accelerometer network around the epicenters. The closest stations who recorded the event were LFTI in Larantuka, Flores, in distance of 88 0.83 kilometers from the epicenter. Yeah. Then, a rapid earthquake intensity map issued after the dissemination of earthquake parameter following our protocol in earthquake seismology in our agency. The PGA, the peak ground accelerations value varied from 0.1793 gals to 74.4388 gals. Despite of LFTI station is the closest recording system from the epicenter, but the highest PGA value recorded by sensor were at IBTA station in Flores, east of Flores, in distance of 117 kilometers with 74.43 gal. While LFTI station recorded PGA of 24, so it's 74 versus 24 gals. Presumably, two mechanisms responsible to this anomaly, local Z effect between LFTI and IBTI, which bring the ground amplifications at IBTI stronger than IBTI. Which bring the ground, second, the forward directivity effect of the focusing of the earthquake wave energy to the earthquake rupture direction provide a stronger force effect to the IBTI stations. Yep. Conducting Indonesia Tsunami Early Warning System Protocol, magnitude larger than magnitude 6.5 with any parameters that potentially triggering tsunami will propose to tsunami warning issuance. The warning should be disseminated in maximum 5 minutes after the main shocks. Tsunami modeling based on earthquake input parameter, generating forecast zone of impact areas. In this first tsunami modeling, maximum wave height was predicted to 0 to 0.5 meters. Following the first warning bulletin, 14 regions in South Sulawesi, East Nusa Tenggara, and Southeast Sulawesi province were warned at the highest warning level. 7 regions in the epicentral vicinity were warned at the second warning level. They urged to inhabitants to leave the coastal areas. Furthermore, we update the modeling. The second updated tsunami warning disseminated at 3:39:29 UTC based on the update of earthquake parameter to magnitude 7.4 together with the result of the moment tensor estimations. The bulletin comprised of sharpened specific warning to 4 regions in the East Nusa Tenggara province, containing estimated time arrival to the first wave of tsunami will be on 3/2022 at the east of Flores. The maximum estimated sea level height was 0.5 meters. I would like to present you our tsunami early warning timeline. This is the protocol at T3/2023, the main shock of urgent time, the first parameter. The second is the tsunami early warning issuance at the first time on 3:25:00, which means that less than 5 minutes. Then, tsunami early warning bulletin number 2 with updated parameter and estimated time arrival. Then we moving forward to tsunami early warning 3, which is containing the confirmation of sea level monitoring. And in several hours after the main shock on origin time, we issued the tsunami early warning 4, which is contain the end of the warning. Does the warning is real or not? At the time, 2 tide gauge facilities around Flores Island inform fluctuation of sea level. There are 0.06 0.07 meter at Marapokot and 0.07 meters at Rio, which confirmed the presence of minor tsunami. This information underlying to decide the issuance of third tsunami warning bulletin, which contained the confirmation from the sea level. Furthermore, observing 1 hour and 10 minutes after the third tsunami warning issuance, the tsunami warning ended. Then we conduct advanced relocation technique. At first, by initial catalog, vast majority of the crustal event at shallow depth of 10 kilometers, following the automatic location procedure of SESCOM-V. Event, after relocation method by HypoDD, we use the HypoDD, the distribution of majority at 10 kilometers depth still prominent. There is no seismicity less than 5 kilometer axis, which indicate that the fault system is probably buried by thick ocean sediment. One other possibility that the fault is located between two geological features in the north and south from the fault line. Hypocentral distribution indicating the planar structure of two moving blocks penetrate up to 50 kilometer depth. Generally, the source mechanism following structure pattern from the epicenter point to the left side. The mechanism merely following the adjacent geological structure of Walania Fault were observed by Grange and Davies to be strike slip. Since then, we confidently suspect that the geological structure who responsible for the generation of magnitude 7.5 earthquake are the continuation of Walania Fault and Selayar Trough. The seismicity turning down in latitude reaching Lesser Sunda Island at right part of the main shocks, locations by mean of the eastern part of the main shocks. At the edge of the bending, source mechanism are thrust. Then, at the southernmost seismicity area, the source mechanism following the major pattern of strike slip movement. We presume the tectonic driven force between the edge of bending seismicity responsible to provide pressure force resulting to the thrusting fault mechanism. Different source mechanism patterns also indicating multi-segment rupturing process. 4 major segments are obviously feasible. Yeah. Since the occurrence of magnitude 7.5, the following aftershocks earthquake increase in quantity. Until 8 days after the main shocks, total number of earthquake reaching 750 events. It's quite incredible. It is a record at the time. Even on January, we record more than 1,000 aftershocks. Moreover, by examining spatial context seismicity migration, we identified 4 major segments which strengthen our previous thoughts. In the first 1 day, the seismicity migrate to the lower longitude by means of the geographical to the west from the epicenter. Then, we do our aftershock observations. The aftershock decay distribution following the empirical UTSU formulation without any observing of large event that might produce outliers on the parabolic curve. By using UTSU formulations, we then predict the aftershock productivity will be N by means of producing 0 aftershock at 45 days after the main shocks. Okay, we're looking forward to have a continuous collaboration and data sharing with CTBTO for saving human life in the future. And thank you for your kind attention.
Thank you so much for the very nice presentation about the tsunami and this early warning system. And then also for using the data, the concrete use of the data that we can follow that on that your presentation that you are really using data from the IMS stations. That's very good that for us.
Exactly, yes. This continuous data from 6 CTBTO stations we incorporated in our seismic system. Yes.
Yeah. But I would like to come back. Just I have a thing that we have 1 minute. Do we have a question from the floor here? Yeah, one and then second there. The first is for here, in the front here, waiting for the micro. Yeah,
Okay.
go ahead.
How is it possible that you got 5 warning signals within 2 minutes and the number of deaths were still as high as 16,000 plus? Is there any reason for that? Is it that the warning signals were not given early enough to evacuate people, or is it that your machines were not very efficient to detect those signals early?
Okay, thank you for your questions. May I directly answer the question?
You can answer it.
Yeah, we do less than 5 minutes issuance of tsunami warning, but the parameter sent out earlier than that. We have 24-hour observation system, which consists of 7 seismologists per 1 GT. And about the damage and the people evacuated, and the victim, of course, at the ground shaking, while the earthquake happened, the strong ground shaking, of course, there's no warning before. In this case, but today in Indonesia, our agency, developing earthquake early warning system, which gives you a warning before the ground shaking, and also the quality of the building also is one key factor of the damage, and also the strong ground shaking give you very, is a one also key factor for the damage. Yeah.
Okay, one other question. Okay, go ahead.
Thank you for your talk. Did you observe any foreshocks before the main shock?
Okay, we don't observe any foreshocks before the earthquakes. Some part of Indonesia have its distinctive earthquake patterns, which have a main shock and aftershocks. In some parts in our region, there are foreshocks. Generally, big earthquake are preceded by foreshock, but in this area, there's no foreshock before. Yeah.
And for how many aftershocks were you able to compute the moment tensors?
We don't need, we just could compute after we have first parameter of the earthquakes, at least above 1 degrees from the epicenter, or 1 or 2 degrees, we start to compute the moment tensors, and then we disseminate the parameters. Yeah, but the stability we need more and more, of course. For more incoming data, we expect more stability to the moment tensors inversions. Yeah.
Most of them were strike slip.
Pardon? Most of them are strike slip, but at the edge of bending, they are truss. So I observe just like 4 different segments with distinctive kind of patterns mechanism, source mechanism.
Thank you.
Thank you very much. Yeah.
Thank you so much. Maybe I will have one more question, but I did not see here. You're the director of the BMKG. But maybe you can talk on her behalf on that.
Yes.
So, during the opening ceremony, she was talking about these 5 minutes that you mentioned here also, and then why you are not able to, not to predict, but to warn the people about the tsunami that occurred in this region. Well, she mentioned that you are not able to.
That's kind of different case at that time. The tsunami happened at the Sunda Strait, where the Krakatoa seamount located. Yeah. At that time, we don't put our instrument to monitor volcano, because volcano are responsible by another agency.
Right.
That's
okay.
that's the
This
case.
is belong to the BMKG.
Yes, now
okay.
the BMKG only the tectonic, and of course I wonder if all of volcanic and tectonic are beyond are on our responsibility, but now we have a separate agency to do that.
Okay,
Yeah.
now I got this now. Okay, good. Thank you so much. Any more question? Otherwise, we'll thank all of you for the presentations, all of you also to be here, to listen to that, to follow that, and then let's meet together here after 1 hour. Have a good lunch. Bon appetit. All right, good afternoon, ladies and gentlemen, and I hope that you enjoyed the lunch, the dessert, and the coffee as well, because because inside it sometimes it's hard after the lunch, and then also with the weather outside, it's very hot and very dry, so that we need to take a kind of refreshment sometimes. And on top of that, coffee is the good point for that. So today, this afternoon, we'll have 3 presentations ahead of us. The first will be done by our colleague here. His name is Usama Kadri. He's from the aerospace engineer and associate professor of applied mathematics, Cardiff University in the UK. He's gonna talking about the real-time early tsunami warning system by acoustic gravity wave theory. So he's coming from, okay, I said it before, he's coming from UK, and then please go ahead.
All right, thank you. Yeah, I'm gonna try and take you the next 12 minutes for a journey on state-of-the-art early warning system for tsunamis. Should I press here, or is it? It's gonna start. All right, yeah, thank you. Yeah, they're using acoustic gravity wave theory. So I'm gonna very briefly tell you what acoustic gravity waves are, and then we move to a little bit of a scientific background. I'm gonna show you a few examples on the operational software that we've developed, and then leave you with some concluding remarks. It's not working. It's not working. All right, so acoustic gravity waves are low-frequency sound waves, and very long waves. Can be tens of kilometers in length. They travel at the speed of sound in the medium, and they carry information about the source. The different applications for acoustic gravity wave theory, and our focus here is on real-time tsunami detection. Can we hear acoustic gravity waves? Well, it depends on the audible range. These are very low frequencies, so if we could actually make it 40 times faster, then, okay, can't hear anything. It's a creepy sound, and it's even creepier. It's not working. Don't worry about that. It's something that to improve next. You can hear it here. Can you hear it there? Okay, now you can hear it. It's like a screaming sound, and it's even creepier in the atmosphere. It's metallic sounds. That just it runs by itself. So don't touch it at this moment, and it should work. So heavy metallic sounds. That's why we call it apocalyptic horns. Can we visualize acoustic gravity waves? Until recently, until last year, actually, we used computer simulations to visualize them. But last year, after the Tonga eruption, you can see on the satellite here, if you look carefully, there's a white ring propagating radially. These are not shock waves, as many think. These are actually acoustic waves. You would see them again. You have an opportunity to see it again now. You see this white ring, which is propagating the reflection of the sound waves. You can also see it. You can also see it here in this simulation. Well, on the left is actually from satellites, and on the right is also, you're looking at the decoupling between the acoustic wave and the tsunami that was generated by the acoustic gravity waves in the atmosphere in this case. All right, so how are acoustic gravity waves generated? They can be generated by volcanic eruption. They can be generated by impacting objects on the surface, by electromagnetic waves, by nonlinear interaction of waves, and by a submarine earthquake. So a little bit about real-time detection of tsunami. So when you have an earthquake, you need that uplift or vertical motion in order to actually generate a tsunami. Acoustic gravity waves will travel at 1,500 meters per second. So by the time the tsunami traveled 100 kilometers, the acoustic gravity waves already traveled 1,000 kilometers, and they carry information on the source. In fact, they can couple with the elastic layer and makes them even faster, so twice the speed. So the information about the source is arriving at faster speed. At the heart of the early warning system really is an analytical work that we've developed 5 years ago. The solution that we had is an analytical solution, is an explicit solution. It's a very elegant three-dimensional solution, actually, and that is the strength of the calculation that we make. Because it's analytical, it's explicit, all you need is the parameters, and once you have the parameters, then you can do calculations quite fast. You can make all kinds of combinations for multifolds. For example, here you can see the first column is an analytical solution, takes seconds to produce, compared to the numerical solution, which can take minutes or even hours to produce. The analytical solution, also the gravity part, which is the tsunami part of the analytical solution, we're quite satisfied with the comparison with Dartboy's data. All right, so because the analytical solution is explicit, then once you go for the inverse problem, the inverse problem becomes quite straightforward. The inverse problem basically says that, okay, now you have that pressure field, which is given from a hydrophone recording, for example. Can you tell me the properties of the fault? And this is what we've done here in the inverse model. There are other models. I can't really talk about all the models, but at the heart of our technology is the calculations using the hydrophones, the recordings using the hydrophones. Our approach is complementary, so we've already implemented and integrated also Dartboy's data to be considered as an independent model for verification matters if the data is available, but we're also looking into satellites and also smart cables. This brings me to the early warning software that we developed. We try to make it as user-friendly as possible so operations people can use it in warning centers. I'm going to show you now 5 examples from this software, but in principle what the technology can do is detect using the hydrophone data, it can detect the event, it can analyze it and disseminate to authorities. So the 5 examples, I'm going to start with a full operational example. All the data that you see here is real time, and it's real data and it's in real time as well. So at first we have an epicenter. The epicenter is the yellow star there. You can see these gray dots. These are basically some kind of hotspots that we call. You can think about this as where the authorities they want to assess the tsunamis at this point and these locations. We started, by the way, there's a machine learning model there. It's another model that we use. It's another independent model that we use just to tell us if there's a tsunami or no tsunami, but it cannot tell us what is the size of the tsunami at these locations. At this moment, you see that we get a warning at some hotspots and pending at other hotspots. So basically, the initial stage, and this is just before the hydroacoustic analysis had started, we can distinguish between the different areas that have more time for evacuation or less time for evacuation just based on the arrival times of the tsunami. Now, once we have the hydroacoustic data, and let's say that we have it right now, then we apply the inverse model. The inverse model can be applied completely automatically, but if you're trained, if you know how to deal with it, you can also do it manually. And once you have the properties from the inverse model, again, if you're trying to do it, then you can also refine things to get better results. This is not part of the simulation. And then you can apply the direct model, right? So once you apply the direct model, what is calculating right now in real time using my just my laptop, right? So it's not a super machine or so. So the direct model, basically what it does right now, it calculates globally, all the points globally, not for a specific region. And as you see here, all these hotspots now are green, and you get this list of information that everything is normal. So you might have a tsunami, but the tsunami is not sufficiently large to initiate a warning. You can see also at coastal areas, coastal areas it's a 50 meters depth, that's a detail. You can see the relative heights on these points, but you can also move into a decision matrix way, which shows everything is green, there is no tsunami in any of these locations. By the way, the hydrophones are the circles, the blue circles, and the triangles, the green triangles are dart buoys. Now, in the case that the data is already in the dart buoy, you can press on the dart buoy, and first of all, these are the calculations from the model on that point, because we already calculated that. Now, if you press on the dart data, if it's available, then you can compare the results also. This is a second way of comparing the results, and in this case, it oscillates around 0.002 meters, which is a good result. And what is even more exciting is that you can, on the fly, you can add a new hotspot, right? So I'm adding a new hotspot right now, well, it's pre-recorded, and then you can press on that and you get the results. Because once we've solved the direct problem, we've solved globally. So everything is calculated then, right? Okay, in the next example, this is from the Sumatra example. I'm just going to show you the results here. Just a reminder that it was in 2004 and it consumed the lives of about 250,000 people. As you see here, the decision matrix shows everything's red, and in some places 3 meters, even more in terms of height, at 50 meters depth. The next example is to show that we can prevent also false alarms. In this case, we have the Alaska famous case with the magnitude of 7.9, which did not result in a tsunami eventually, but it was a big evacuation as far as I remember. So in fact, here the machine learning is quite interesting because the machine learning shows immediately that you have 0 there means that there is no tsunami. But anyhow, we're running the other models in parallel, and the other models also show that everything is green. There's one place which is advisory, but in general, it's a good result as well. This example is a purely educational example. The reason that I took the Mediterranean Sea, because when I presented this this work originally 2 months ago was for the steering committee of the UNESCO, is the regional meeting, and I wanted to do something which is related to that region. Now, if you can just go forward to 3/4. So basically, what you can do, you can also use it, you can put the input there yourself, right? And you can use it for educational purposes, right? And studying different scenarios and so on. Okay, the last example that I want to share is how the software operates on a station, on a multi-core station, right? It's not a supercomputer, but it's a good multi-core station. Once I say go, don't blink, all right? It's going to be fast, right? Okay, so I'm connected remotely to the stations, all right? So now, go. It starts right now, so the acoustic data is there. It starts the calculation for the hotspot model, the first model. All right, that model is done. Now the inverse model is done, and then the direct model is working, and then the direct model is done, right? I started the calculation at exactly 1 minute before 5 a.m. So it's 0 seconds there, I don't know if you can see that. And the whole calculation took, as you would see, 17 seconds. And that was done remotely, actually. And I did that later on. It took less than 15 seconds. And the ambition is to go 1 digit in terms of timing. Thank you.
Thank you so much. So in terms of tsunami warning, it's very interesting for having that. Thank you so much for that. Any question from the room? Yeah. Go ahead.
Thank you, very nice talk. And I would like to ask about the machine learning technique that's used in that sections. In particular, could you please elaborate more about in which section in which sections you use the machine learning technique? And the second question is, how long is the time from the parameter to the impact areas have been calculated?
Okay, so machine learning model also feeds on hydroacoustic data. So everything that I showed here feeds on the hydroacoustic data. We used 200 past earthquakes that some generated tsunamis and some did not generate tsunamis to train the model. And we're currently working on a new version with 50,000 cases. The time it takes is much faster than the other models, but the problem with the machine learning is that it can tell you if you have a tsunami or not. There are many problems. One of the problems is that it can tell you if you have a tsunami or not, if you are within some good range, right? Because if you go higher scales, higher magnitudes, you don't have sufficient number of data that you can train it in a good way. But even if within that region, where you have sufficient data, it could tell you that you have a tsunami, but it doesn't tell you what is the size of the tsunami. So like the first case that I presented, right, there was a tsunami really, but it was a very small tsunami. So it would be good to, for example, in the case like the Alaska case, when you don't have a tsunami, it tells you there's no tsunami. The other models say there's no tsunami, and they're completely independent, and your confidence is high in the results. So you don't need to issue an alarm in that case. But in terms of, it's much faster than the other models. It's fractions of seconds.
And about the second question?
How long is compute from the earthquake parameter to the impact zone areas of the tsunami? It's very fast.
I can tell you how long it takes from once we receive the hydroacoustic data, yes. Right? Because everything else from the time of the eruption itself, it depends where you have the hydroacoustic location, the differences in locations, and so on. The travel time that it would take the hydroacoustic data to reach and then the recordings reach the software. But I can tell you from the time that we receive the hydroacoustic data, it's just what you've seen here. So it took 17 seconds on that remote machine.
This is the last question from El Gabri.
Thank you for the interesting talks. I have one question, consists of two questions. The first one is about possibility of landslide tsunami. Is it possible to predict it using your code? Landslide tsunami.
That's a very good question. So let me answer this and then you move to the other question. The strength of what we've done is that we don't really care about the source in some sense, right? So I need to be careful here because we do use the fact that you have an elongated source. But the idea is that we talk about some effective elevation of the water level that would result in the compression of the water, which generates the acoustic gravity waves, right? We don't really care what made this effective elevation, whether it's a meteorite, landslide, or whatever. Now, for accuracy purposes, it depends on the shape. So the mathematical solution needs to be revisited maybe in order to refine around the different geometries.
The other question about the Mediterranean case, whether you have some verification, because from what you showed firstly, I can see there is some discrepancies between the current models we already knew about it for 365 and your results. So did you have any verification for that?
No, not at all. I mean, it took me something like 10 minutes to look into this case. I just put some parameters. I would be more than happy to see what parameters that you have there. Maybe we can use these parameters and see what kind of results we have and compare the results.
Okay, thank you so much. Thank you again. Thank you, Kadri, for this very interesting. Maybe I have a question to you, but later on, after this, I will go back to the inverse problem. Okay. Yeah, the next presentation will be done by our colleague Ismael da Costa from Timor-Leste. He's working at the Civil Protection Security. And again, he's going to talk about the enhancing of tsunami detection and early warning in the Timor-Leste.
Thank you. Very good afternoon. Dear moderator, dear colleagues of the speaker, dear participant conference, once again, very good afternoon. I would like to share with you the very important occasion today on enhancing the tsunami detection and early warning in our own country. The point I would like to share with you, I would like to brief you Timor-Leste, glad. When I was, during the 3 days I was participating in the conference, many of our colleagues asked, where are you from? I'm saying I'm from Timor-Leste. They say, where is Timor-Leste? Today, very important opportunity to inform, to brief you Timor-Leste. And then secondly, the justice overview. Third, national civil protection emergency aligned with early warning system. And four, need a strong tsunami detection and early warning. Lastly, conclusion. Timor-Leste, the younger country in Asia, and second country in the world. We was independent in May 2002. We are under by the two administrative colonized by the Portuguese, and secondly, our friends from Indonesia. Timor-Leste population 1.4 million, and then most of our population living in capital of Timor-Leste. Timor-Leste located between Indonesia and Australia. We are in the middle. The administrative division by our 30 municipality and one special region, only one region enclave surrounded by our neighbor Indonesian territory. Demographic profile, 50.8% male and then 49.2 female. The population grew up 2.1% in 2022. It reached rate 30.94 births per 1,000 population, and death rate also 5.6, and then median age 20 population below the 8 year. Language, we are colonized by the Portuguese. We use Portuguese as the official language. English and Bahasa Indonesia are common working language. Our region is Catholic, the majority, and then followed by the Protestant and the Muslim, 0.2%. Economically, we are dominated by our oil and gas, 90%. Timor country grow domestic production. We are living in under the below the property. And then secondly, I will brief you with an overview of disaster in Timor-Leste. The key vulnerability, trend from the November, normally we season monsoon, raining strong with cyclone regularly, damage our and destroy our property. And then cyclone occasion also developed during April, May, and moved to the southwestern direction. A tropical cyclone occurrence in Timor-Leste around 0.2 per year. And dry also affected our country during the El Nino. And then Timor-Leste located in the high seismic activity region, the earthquake and tsunami. because we are located in a ring of fire. And implication to the disaster risk management, increasing rainfall in vulnerable to the population living in along the high risk area. Flood also, and landslide extensively damage our infrastructure and road. Increasing the flood and dry affected our food security. We estimate 50,000 individually can be displaced during the flooding episode. Delhi as the capital and the sea power high risk of the population destined and explores flooding and tsunami. The region earthquake map visually we are record in 2016 till 2022. We are working closely with our colleagues from neighbor Australia, Indonesia. And I would like to brief you also the historical. We also faced some challenge on tsunami during the Portuguese colonization. Also, we are affected by tsunami in 1857. Also, with our during the Indonesian administration in Timor, 2 episodes affected tsunami. And then lastly, when we are restored our independence, we are also affected tsunami in Delhi. Most of them located in the north of our island. Cyclone also is very effectively across to our territory every year, like I mentioned before. Based on the source by the World Bank, Climate Change Analysis Portal, the just overview summarize of Timor-Leste, where informed the risk index in 2023, we are the medium class. The hazard explores, we are 101 ranking, and then vulnerability, we are 65 ranking with the other country around the world. And the lack of capping capacity, we are 49 ranking. Aggregate annual natural hazard occurrence in Timor-Leste. Most of the risks we are affect Timor-Leste, the flood, followed by the epidemic, earthquake, dry, and strong wind. The need strengthen tsunami detection, early warning, to make some action to take some prevention for the future. I would like to inform you, like I mentioned before, Timor-Leste islands located between the 3 major plates, the Eurasia plate, Australian, and Pacific. Between the 3 major plates induce the high seismic in Timor region. The current tsunami monitoring and alert situation, we are aligned with our civil protection emergency plan, emergency response plan. We have 3 types of emergency response plan. The first response, we are guaranteed with our own institutional capability. And second response, we are guaranteed with our national capability. And then third response, we are collaboration with our multinational humanitarian support during the disaster. And then currently, we are supporting by our neighbor, Indonesian monitoring agency, BMKG, provide us some warning, some monitoring and alert. Our own meteorological and then tsunami service provider from Indian Ocean. Under our National Command Operations Center, will be receive messages and then continue to alert to our municipality and then village level in our national system. Gap of challenge with the current system we are faced today. They need automatic monitoring, particularly major earthquake with the general tsunami. Secondly, stabilized alert system community level to ensure the timely evacuation warning. And lastly, collaboration with the academic, science, and establishing early warning, develop the structured, non-structured mitigation strategy. One of the reasons today we are present here to request more some assistance from our CTBTO. And the link IMS data with the Civil Partner Authority, one of the main important, also main challenge, how to integrate the science and the management of disasters. The important to integrate important but technical investigation, forecasting model, hazard assessment, probability model, and then the disaster management will take some action on prevention, mitigation, preparedness, response, and recovery. One of the important subjects, important topic, we are take some consideration on that. Enhancing understanding the risk, civil protection would like to sorry. Can you? Sorry. Please apologize for next. Yeah. Enhancing the understanding of the risk, civil protection, I would like to work with the CTBTO to help us to understanding the earthquake, tsunami, historical event, the impact of the factor, mitigation, population, climate change, impact modeling, also the high risk, explorers, earthquake, and secondary hazard, vulnerability, population, community, economical asset, activity, explorers, and critical infrastructure, and cultural heritage, map and risk assessment. On our conclusion, lastly, I would like to inform that the earlier my presentation, we are in the medium disaster risk level by the World Bank source. And the climate-related hazard, El Nino, we are, Civil Partner Authority will to work with the CTBT to develop a risk reduction strategy, intervention on mitigation, on geotectonic hazard by enhancing the monitor and detection capability. And civil protection will partner with to invest the capacity building in national, design a particularly effective the early warning system, develop national and operation command center, identify the pre-position and strengthen community resilience, geotectonic and climate change for the future. Thank you and for your kind attention.
Thank you very much, Ismail, for your presentation. Any question from the room? Yeah, please go ahead. Mike?
Thank you very much, Ismail, for your presentation. What is the correlation between these vulnerabilities that you indicate that 50%, about 50% of the vulnerability is related to flooding? And this is related directly with tsunamis or with other events like rivers or another sources of risk?
Yes, the historical, we have the tsunami affected Timor-Leste, but currently the higher risk of the disasters in Timor-Leste, the flooding. Because the Timor-Leste near, close to the the normal is we have two season in Timor-Leste, rainy season and dry season. Because of the climate change, they affected to our season. It's not make some balance how we can manage when there's some disasters happen. And then we need more some critical science on that, how we can manage. And then we are learning from the other country, other neighbor, to improve more our national capability on prevention on disaster.
Thank you so much. Let's move now to the next presentation, the last one that we have today. It will be presented by Golam Rasul. He's coming from the Bangladesh Atomic Energy Commission. And again, he's talking about importance of the IMS data for the Tsunami Warning Center in Bangladesh. By the way, for Timor-Leste, we can talk later on about the use of the IMS data. Yeah, thank you so much. Yeah, please, go ahead.
Okay, thank you very much. Already the chair mentioned my name and my designation and with my affiliation. I'm from Bangladesh Atomic Energy Commission. And why we are here is actually we have the CTBTO seismic station in our country, but now we want to improve the activities of this station to disseminate the data to other organizations like Tsunami Warning Station. So first I want to show the outlines of the presentation. Is like Timor, I want to show the country overview, then geographical and tectonic setup of Bangladesh, possibility of occurring tsunami, one organization, Bangladesh Meteorological Department, and their activities because they are now on the position of tsunami warning setup. And we, the Atomic Energy Commission for CTBTO IMN station, and finally, tsunami warning agreement with the CTBTO and opportunity for NDC. Actually, my presentation mentioned the role, the importance of IMS data, but I do not present any IMS data is on research basis or IMS data presentation. I will show actually the present setup and present condition of my country and how we'll improve it for our future program. So this is Bangladesh map. Actually, very small area is 147,570 square kilometer, but the huge manpower, 169 million population over there. A small country surrounded by India is mentioned here. It's a very small by red color. The geographical location of my country is at the northernmost part of Bay of Bengal, is a funnel shape ending at the southern coast. Regional tectonic setup of Bangladesh with the respect of plate configuration, the map shows that technically Bangladesh is in a region where the junction of Indian and the Eurasian plate making active zone of the world. And the Indian plate is moving 6 centimeter per year, whereas Burmese plate is moving in the different direction as 2 centimeter per year. And the zone is showing that the quite frequent earthquake active occurs along the plate margin of this region, some part of which is under the ocean, stretching down to one of the most tectonically active area in Indonesia. Therefore, possibility of earthquake in the ocean is likely to occur in any places of the region that can result to tsunami at the area. Possibility of occurrence in tsunami in Bangladesh. So in the map we observe that Indian and Burmese plate are moving in different direction and they're changing their direction in different velocity. It shows a subduction zone in active and it could generate a devastating tsunami in near future. Another major concern is the North Andaman Teknaf subduction zone seismic gap. According to experts in our country, they mentioned that there is a 600-kilometer seismic gap along the subduction zone that is stretching north of the Bay of Bengal from Andaman to Teknaf. Enough energy is stored in the seismic gap to cause a strong earthquake in our country. And if it's happened under the sea, then the earthquake can create a tsunami. Experts fear strong earthquake and tsunami in our country. Moreover, the expected rupture of the Andaman Teknaf seismic gap is run from northeast to southwest direction. So this is the historical tsunami happened on the 26th December 2004, where the Indian plate and Burmese plate subduction zone ruptured, released energy, and create earthquake. And with this earthquake, directly affected the tsunami in the southeastern region and the yellow color countries. Bangladesh is one of these countries. But during that time, what happened? A massive underwater worth measuring 9.3 caused a huge tidal wave or tsunami in the western Bay of Bengal. It was the second biggest earthquake recorded in the region and was caused by friction between the Indian and Burmese plate. But Bangladesh was safe during that time because the direction of the friction was north-south, giving rise to a east-west moving of wave. But now, what the experts are claiming that there is a Teknaf Andaman seismic gap that is stretching 600 kilometers, and the expected rupture of the seismic gap runs from northeast to southeast direction. So if a tsunami is generated in the Bay of Bengal from this subduction zone, it will directly assail the coastal areas, including our coastal region. A huge population is living there, along with the West Bengal and Odisha of India. So now I will talk about the organization. This is Bangladesh Meteorological Department is our meteorological organization of Bangladesh, and this department is authorized monitor earthquake and tsunami by Bangladesh Meteorological Act from 2018. So before 2018, the earthquake and the tsunami was not monitored as per any specialized organization. From 2018, it was mentioned, and it was a rule by our government. And the meteorological department are a small setup. They are using only 10 seismic station, countrywide distribution of this station. How they work, they're getting data from this station, and all the stations are in land side. And this is the topology of their work. And there is no designated tsunami warning center yet in Bangladesh. So how Bangladesh is issuing the warning? BMD issuing the tsunami warning in Bangladesh on the basis of information from IOTWC, Indian Ocean Tsunami Warning Center, Indonesian Tsunami Warning Center, and Australian Tsunami Warning Center. And there is the Atomic Energy Commission in Bangladesh. We have an international monitoring system, the auxiliary station AS007 at Bariadhala, and under CTBTO, we are monitoring this data. This is our station. It is above 70 feet above the ground in the hilly area. And a signatory country we are since 24 October 96 and is rectified on 2000. But to accomplish the goal, the station started its data transmission to IDC in 3rd February 2011 and has been activated on December 2011. And this is the history of technical cooperation of CTBTO. It started from 2010 and finally it updated in 2017. So this is our station activated in 2011 and the final figure of this station. And our national data center that is established in the capital city. NDC box is supplied and installed during this upgradation, and we are requisition is submitted for CBS installation, and the executive director already visit on October 2018. So tsunami warning agreement with the CTBTO. CTBTO and UNESCO is a partnership in disaster management. So Asian tsunami, though is create a tragedy, but the tragedy on the situation brought awareness to the need of the global alert system in order to minimize death associated with the tsunamis. The CTBTO and the IOC UNESCO agreed to share effort and data in the field of tsunami early warning system following the 2004 Indian Ocean tsunami that kills more than 230,000 people. Tsunami warning agreement with the comprehensive Next Treaty Organization is needed for strengthening the country's ability to issue further and more precise safety warning in case of tsunami. As the auxiliary station of our country established station is designed for tsunami warning system, so we submitted our proposal to our permanent mission to discuss the matter with the UNESCO. Because Bangladesh does not have any tsunami agreement yet, however, as was CTBTO, the auxiliary station established in Bangladesh is designed for tsunami early warning system. As Bangladesh is hosting the IMS station and the NDC since 2011, so hence it invited to establish a tsunami warning agreement with the CTBTO, thus benefiting from relevant IMS data to enforce and complement early tsunami warning system. So considering the authority of BMD, the department is responsible for tsunami warning and the establishment of CTBTO under BSc, IOC UNESCO can think to establish a tsunami warning center in Bangladesh in collaboration with CTBTO. So importance of IMS data for tsunami warning is very important, we all know. So in identifying depth phases, horizontal earthquake rupture, and LP and BP estimation for its magnitude. How NDC in Bangladesh can contribute in tsunami warning center in Bangladesh? Could be strengthened for analysis event by establishing capacity building system installation. The CVS establishment could be helpful in integrating data acquisition, processing, and analyzing using the NDC in above software and investigating different incident events. Relevant officer from Bangladesh Meteorological Department, Tsunami Warning Laboratory of University could be added as authorized user of NDCBD for having access to IMS data and IDC product, as well as to be built a combined national team for this purpose. And now the proposed is our present status, the NDCBD. We have only one PPOC, 2 principal user and 7 regular user, a very small setup, and the regular user all are from outside. So we have a scope to adding more user, a scope of analyzing IMS data for civil and scientific application, a scope of analysis defined seismic event for tsunami early center. So the conclusion, tectonically, Bangladesh is in the junction of Indian and Eurasian plate, making an active tectonic zone of the world. Possibility of earthquake in the ocean is likely to occur in any place of the region that can result in tsunami in the area. Bangladesh is hosting an IMS station and a national data center, hence invite to establish a tsunami warning agreement with the CTBTO, thus benefiting from relevant IMS data to enforce and complement early tsunami warning system. Strengthening NDCBD by establishing capacity building system installation is prime requisite, and building a national team to work together for different organizations to able to access IMS data for tsunami warning center as well as civil and scientific application. So the proximal test of this presentation is necessity of installation of tsunami warning center and strengthening of NDC in Bangladesh. Thank you.
Thank you. Thank you so much, Rasul. I think that, so you and I will have to discuss also about this tsunami later on. Okay. Following this, because I see that the people that will go into to follow up here is there, they are ready. So we have to move now. And if there is any question, let's have that outside this room with them. Okay, thank you so much for being here. And next time, next SnT.